A very good morning, students. So our next very important topic is the frequency response. So the frequency response, basically the phase response characterization, is done using the transfer function. The transfer function will always be given to you in the question, either in the form of h of n, you have to convert it in the form of h of z. So we have divided our phase response characterization into three basic parts, that is minimum phase, maximum phase and mixed phase. Now what are these? Let's understand. Whenever a causal stable, I hope as of now you are easily able to understand when I am talking about a causal stable system. So whenever a causal stable linear time invariant system with transfer function h of z with all zeros inside the unit circle is called as the minimum phase. So we're going to find out the stability of the system. We're going to locate the zeros. If they are lying inside the unit circle, it is called as minimum phase. Similarly, of a causal stable system with transfer function of h of z with all the zeros outside the unit circle, it is called as maximum phase. Lastly, a causal stable system with at least one zero inside the unit circle and at least one zero outside the unit circle. It's called as mixed phase. So last point, minimum phase system are important. Talking about these systems because they have a stable inverse g of z, that is 1 upon h of z. You can convert between minimum, maximum, mixed phase system by cascading all pass filters. That means you are going to add or subtract zeros, so you can switch from minimum to maximum to mixed phases respectively. Now, how to calculate the magnitude in the phase response? The question will be given in the form of transfer function, that is numerator upon denominator. You will be having your zeros, you will be having your poles. Locate the values of these poles and zeros and convert them into polar forms. And then you will get different values of, suppose the pole is lying over here, your zero is lying over here. Its position with respect to origin first of all you have to find. Then magnitude, that is h of s, and phase, that is angle of h of s, you have to find. So for example, this is the location of the pole from the zeros. So you will be calculating the angles with that is theta 1 and theta 2. With respect to poles, and the position of the zeros with respect to these poles is phi 1 and phi 2. So you're going to add sum of all angle of zeros with respect to P and sum of angle of all poles with respect to P. And this is how you plot the magnitude in the phase response. So depending upon the different locations of poles and zeros, your different characterizations of filters is done, that is low pass, high pass, band pass and bend stop. We're going to further discuss them in detail. Meanwhile, you can go to the slide. So how it is affected, the position of poles and zeros on the frequency response. You're going to notice that the frequency response is obtained by evaluating the value of the transfer function along the y-axis, that is taking s is equal to g omega. Whenever I am talking about the frequency response, if it's in the form of Fourier, I need to replace s by g omega. If it is in the form of z transform, you need to replace z by e to the power j omega. So you're going to notice that whenever this near to the pole, it enhances to the amplitude. This amplitude increases. This amplitude over here increases. And whenever it is near to the zero, the amplitude suppresses. This amplitude suppresses. This is going downwards, this is going downwards. This is going upwards, this is going upwards. This is nothing but your amplitude. So this is how the position of poles and zeros is going to affect my frequency response. You should have verified this all using your SP lab. Now talking about the characterizations. So based on that, your basic 4 filters are in your syllabus. Talking about the positions. So first, talking about the positions of the poles, we have the low pass filter. So low pass filter is nothing but this type of filter passes the frequency from 0 up to some design frequency called as cutoff frequency. After cutoff frequency, it will not allow any signal to pass through it. So this is how you design your low pass filter, and this is how the characteristics of a low pass filter is going to look like. So you can see the position of the this is called as brick wall type LPF. Very sharp cutoff frequency. We need a wall of poles, and the more poles we get, sharper will be the cutoff. So as of now, this you have already done in control 1 by the position of the poles. You have to just define the low pass filter is nothing but which is going to allow the values to pass till certain cutoff frequencies, that is omega c, and after that it is not going to allow. So this kind of filter is called as low pass filter. Next, talking about the bandpass filter. Bandpass filter has gain enhanced over the entire pass band but suppressed elsewhere. That means it will allow the frequencies between two designated cutoff frequencies. That is over here. This is suppose omega 1, this is omega 2. So some designated frequencies, before that it will not allow, and after that also it will not allow. This is band pass. It is going to allow a band of frequency to pass through it. And this is how its characteristics with respect to the real and imaginary axis are going to look like. This you are going to draw from the values of the transfer function, positions of the poles. Talking about the high pass filter, that is this one. So what you are going to observe, it passes the frequency above the designated frequency called as cutoff frequency, and if the input signal is less than this cutoff frequency, then the signal is not allowed to pass through it. Right after the designated frequency, it is going to pass the amplitude of frequencies, only the high pass, hence known as high pass filter. Last but not the least, band stop filter. It attenuates all the frequency between two designated frequency. Band pass, what band pass was doing? It was allowing to pass a particular band. Band stop is doing what? It is attenuating the particular band of frequencies between the certain range. So it is going to attenuate all frequencies between two designated cutoff frequency while it passes the other frequency. Hence name as band stop filter. Right? So these are the 4 types of band depending on the position of the poles and kind of the frequency we are going to allow to pass through them. Similarly, in the next is Butterworth filter. These first 4 types of filters are in your module 3, and this fire filter you will find it in your second last or last module, that is Butterworth filter. I thought of covering them together so that you can understand with respect to the band of the frequencies. So we have taken example of low pass filter, one that has a cutoff frequency with certain amplitude characteristic equation. If n tends to infinite, this gives the ideal low pass frequency response. So just look at the characteristics. You have defined all the low pass, high pass, band pass and band stop with respect to these characteristics. Now talking about the Butterworth filter. This type of filter are basically called as Butterworth because its main characteristics is that pass band is maximally flat. The amount of frequency it is going to pass through it, the kind of band it is going to allow to pass through it, till cutoff frequency is maximally flat. You can notice over here. That means no variation in the ripples in the pass band. Similarly, what are the other features you need to notice about the Butterworth filter is magnitude response is nearly constant, equal to 1. You can see that the magnitude is nearly 1 till cutoff frequency. That means pass band is maximally flat. There are no ripples in the band pass and the stop band. And the magnitude response is monotonically decreasing for n is equal to 1, n is equal to 2, 3, 4, 8 and 10 respectively. So these are the characterizations. Substitute whenever you need to find the frequency response of a system. Substitute S is equal to j omega. Then find its values, find the values of poles, look at the position of the poles with respect to the unit circle. We are only interested in the values of h of n, therefore the poles of the low pass filter and those lying on the left hand side of S plane. Frequency response, we have a frequency response since we are going to talk with respect to S plane. So lying on the left hand side of the plane, so accordingly we are going to find the transfer function and plot them. So in your syllabus as of now, this type of explanation is called as Butterworth filter. This much you have to understand first. So make sure you're clearing the differences between the four types of filters, that is low pass, high pass, band pass and band stop, and lastly the Butterworth filters. Thank you so much.